No.
Voy por eso. No. Now it's okay? It's okay now. Good. Very good? Here we go. So I'm going to show flow, which is this, in this list of challenges I've shown in my presentation, I mentioned the single page application opportunity or challenge, and you are seeing many libraries and all in the web. And I want to bring some computing power and developing power to the front end. So Flow, Smalltalk is great for that, well known by you. And with Flow, I'm using Ember and a couple of things to bridge some gaps, so that productivity start to appear or emerge in the developer experience. So that it's in GitHub. It's not even under my user anymore. I put it in its own thing, so it's world. And I'm using this Gitter chat, which has it's better than IRC because it has history and you can search. So, and I'm working on this demo of a pet shop because having a demo of a small little thing that illustrates how do you do a controller, how is the view going to be deal with, and it's a friendly demo, incomplete at this point. And if you take a look, for example, see a feature. If you add here, if you look at the card here, you will see that it should be double data binding. So if you press, it should respond like that. It also, if you do that in the double data binding, it will work for anything. So, and if you press on the card, you will go to another controller which has its own view, and that view is having a subcontroller that is not just HTML. It's a small subcontroller, this one, using a micro template that is in HTML. So I'm not using, even though Amber has the capability of use the canvas like Seaside, I'm not using that. I'm using the HTML that is typical from a designer, and it's going to be loaded with required JS. And it's the list is double data binded too. So when you remove an object from the collection, you see the controller disappearing. Let me stay on this page. Copy that, and now leave. I don't like that one. Here we go. That's the old one. Let's go to the new one. So I'm trying to commit a couple of usability things, improvements in Helios, so Ember gets even more productive. So, for example, if you get this one, this is cart, right? If I want the cart, I'm using the local storage in Chrome to get the model. So I get a cart if I print string here, and if we can inspect it. And this is a cart, and the cart should have products, right? And they are the products. They are not even JSON. They are products already, like Smalltalk. And you can say first, and you can say description, and it should show, okay? So you have Smalltalk there. Let me show you how the controller looks like. You have all the Amber things here, Ember, and here the pet shop. You have the card, like the model, and then you have controllers, which are binding controllers, children. And look at the code, for example. Here it just observes when something is removed, and it reacts. I like very much this action-reaction thing. It's like a pattern I use. And when it's removed, it's just refreshing the controller. So looks like good. And this is when all the templates that are bind receive this on template, which is the callback they get when they are already completely loaded there. And then you can do things like creating sub controllers there. So, okay, that's for the front end. In the back end, we have a Faro, and Faro is using another framework I made, which it's named Mapless, because it doesn't have a map of instance variables for your data. You can see here I don't have any instance variable there in the model, but if I do with the Mongo pool and I select this, we'll find all the products in this database. You will see that these products have actually a lot of JSON data, like, let's see, created on this one, self-created on, and they have the data, but they don't have they don't even have accessors that you just talk at them like magic. Not like magic. It's like I want it to be felt similar to JavaScript prototyping objects. So that's why they look like that. So that's it. That's a start for Flow. I'm using this for a commercial product for a customer in Italy. It's a real project that is pulling the priorities to go and do the commits that move the project forward. But it's everybody's MIT. You're super welcome to take advantage of that and use it for yourself. So there you go. Thank you. Questions?
4 minutes for questions.
Whoa. Okay. Questions. There are questions?
Any questions?
Maybe someone is curious about the templates or something about that. Or?
I don't have a question, but I should say that I think what you're doing is awesome. For two reasons. One, open source small tech applications that are really produced in practical, awesome.
Right.
Two, what Alan was talking about yesterday, I don't know what day it is.
What matters is the insight.
Alan Wishbrock was talking about, small talk was like really, really popular until like the web. The web came sort of like way. So this is like one of those things we can actually bring someone to
Yeah.
practical, usable way.
Yeah.
Anybody can
Yeah. Thank you for bringing that up. Awesome. The idea is that I want startup profile kind of things, or consultants or corporate innovation that want to make a front end that feels like something really, really new, and it should be do with something like this. Okay. Thank you.
other questions?
Oh, that's a good question. Well, I show you that controller, like one controller making another controller. You saw it, that one. The controllers doesn't have to worry about the views. So all that code, it's decoupled completely from Smalltalk, and it's loaded by require.js on demand. And so in everything that is view should be like less of that, and if you take care, your controller should be cleaner. So that's in favor of having less code, but depends on your style and what you are doing. Maybe if you are using, for example, D3 or something that is very, very powerful and verbose, then you have to be wise on how are you going to invoke that for not deteriorating the user experience. You have to use preloaders wisely and things. Good, makes sense? Okay, thank you.
Well, hi. My name is Juan Buletich, and I am the lead developer of Quiz Smalltalk. I talked about it sometimes in previous editions of this conference. I'm also doing a sub-project that is, in a sense, part of Quiz Smalltalk, that is redesign of Morphic 3. Excuse me. This is not quite right. What's the native resolution of this? Like this. Okay. Well, yeah. Quiz includes a deep redesign of the Morphic user interface framework, and I am writing a new rendering backend for Morphic in Quiz. That work is called Morphic 3. I talked about it a couple of times. The idea, the regular renderer in Squeak and Faro and current Quiz is based on BitBlit, and is a direct descendant of the Alto code, in a sense. And it is based, like most user interfaces frameworks, on display coordinates. Okay, you need to know about pixels and classic drawing operations like the ones in GDI in Windows and such APIs. In Morphic 3 is different. Morphic 3 is vector-based. It's based on the ideas of PostScript and SVG. It's independent of pixel resolution. And for it, I wrote a new rasterization engine I call Morphic 3 that has some new ideas on it. And until recently, I wasn't able to publish the code because these new ideas were not protected, and I'm sure someone else would try to patent and steal them. But fortunately, now we have this defensivepublications.org. This is a non-commercial, I guess, in a sense, organization that manages a prior art database for the US Patent Office, and they take for no charge defensive disclosures. And last year they accepted my defensive disclosure on the techniques of Morphic 3, so no one can steal them now, and I was able to publish the current state. It's pre-alpha, it's not really for really using it, but it's good enough for studying it, and it is published in MIT, so you can get it. And the paper they accepted is this. Is very short, just 6 pages. It has no patent legales or academic requirement, so it's meant to be easy to understand. So if you're curious, please Google for it at defensivepublications.org and read it. Well, I think I'm okay on time, so I will now tell you what does this engine do, and a bit why it is different from all the other ones. Regular vector graphics rasterization engines such as Cairo, the first thing they do with the vectors, with the curves we are trying to draw on the screen, is to convert them to polygons, and then for each pixel in the screen they find the intersection with a polygon and they compute the area of that intersection. This is very expensive, and the techniques that they use are pretty advanced, and the code is not easy to understand, and they require serious optimizations to give reasonable speed. And I came with a new idea that is so simple that hard to believe. You will say I am crazy and that everybody knew how to do this before, but I swear nobody's doing it. So I will just show you using the very paper, because I didn't prepare any slides. I apologize. Well, the main parts of the disclosure solution are, this is the curve we are trying to draw. In SVG, in vector graphics in general, we draw curves specifying some coordinates and some parameters to some drawing primitives. This will be perhaps a segment of an arc of a circle. Okay, we could draw it with a compass like this. This is the trajectory our pen will follow. This is how the SVG API also works. It's modeled after that. So we are using a pen this wide of color red, and we do this motion with it over a piece of paper, and this is what we get. Okay? So we can model the pen we are using like a function that has a value that is transparent everywhere except this part where it is opaque. This function is one-dimensional because I assume the pen has a cylinder. Yes, it's like a circle, okay, a circular shape. So it is symmetrical. So this is a circle of this width. Okay, this is the ideal we want to draw. In reality, in a computer, we have pixels. Okay, we have some grid of pixels that can be any size because that curve is not specified in terms of pixels, but in terms of some real numbers, floating point numbers, at any scale with respect to some pixel grid. Okay, so we have the curve we want to draw, and we have the pixel grid where we want to draw it on. Okay, now I'm using some signal processing theory that I won't go into too much detail here, but the idea, the most basic idea of the sampling theorem is to say that a digital signal, okay, a discrete signal, not a continuous function, cannot change faster than some limit. Okay? So, how do we honor that limit with our pen? Well, the easiest way to do it is, instead of jumping from transparent to opaque in zero space, we just give it some air distance. It will travel from going to transparent to opaque, and to opaque from transparent. Okay? So this is opaque, and this is increasingly transparent at the sides until it is completely transparent outside. That is the model of the pen we will use in this engine. So now we place that curve draw with that pen on our pixel grid. Okay? And the next thing we do is to find for every pixel, or for some pixels that we know that will be affected, the distance from the center of the pixel to the real trajectory of the pen. I just draw these arrows for the external pixels, not to mess too much the graphic. But here you see how for this pixel this gets increasingly opaque, and we sample at this point at the center of the pixel where we evaluate the transparency function, and we get this value, almost transparent. This other is closer to the trajectory of the pen, so it gets a much less transparent, opaquer, and don't know if that word exists, value. And all we need to do is to use this transparency level for alpha blending the color we want to draw on that pixel. And that's all. And the paper finishes. Okay? There's nothing else. So, please, not yet. Do I have a few minutes more? Here comes the code. Okay? I will do it as fast as possible. We have I currently have two implementations of this. The real one that is called Vector Canvas and Vector Engine, but I was asked by some friend to do a simplified version for teaching purposes. The only difference is that this one doesn't know about morphic, okay? Doesn't know about morph at all. It doesn't handle gradients, and it doesn't handle dashes strokes, okay? So, this is some of the things we can do with this engine. This is a very simple example, okay? It's a Bezier curve, okay, drawn with these parameters. But the interesting part is what it means to draw a Bezier curve in this engine. Well, it means to prepare a few variables to do the math for the Bezier curve, do an iteration of a number of hopes, of shams, and just apply the formulas for the trajectory for the Bezier function, and add current point to trajectory. Add current point to trajectory is essentially, this is doing with the subpixel sampling, so it's done differently for the red, green, and blue subpixels. And the important part is that we iterate over the pixels we know that can possibly be effective, and compute a distance to the trajectory, and try to minimize it as going through several steps in each pixel. And we just keep the minimum of that. And the same for green, and the same for blue. So this computes those little arrows I showed you before. After with all the trajectory, all we need to do is to alpha blend the results on the screen. This is done by iterating over pixels. I also compute edge crossing for doing fields, but I won't go into that now because I have just a few more minutes. And we call this method that does the actual blend. The actual blend, this is blend stroke and fill. The one I meant to show you is blend stroke only, that is the simplest case that I showed you there. All I do here is to iterate and blend. And blend means pick the computed alphas for the pen and just blend, okay? This is the classic alpha blending formula, and that's the result. I'm not doing intersection between polygons and pixels. I'm not dividing the curve into polygons. I'm not having tree-like complex structures for storing the stuff and doing set order of the stuff to the computation. It's many orders of magnitude simpler than what Cairo is doing. And the result, the projector is not really good for showing the quality of the results. You should look at them at the LCD screen, but the results are pretty good. This is a new auto hinter that Adobe published for free type last year. They compare the new version with the problems they had with the older ones, and this is the new one that they say it is much better. And this is the result I get, without any hinting at all. On the LCD, the difference is even bigger. The weight is better, blacks are black. Here you have a lot of stuff that gets grayer. The weight of the strokes is constant across any size, and there are no traces of reddish or bluish shadows like Microsoft ClearType. So I think it's clearly better. Well, that's all. Thank you.
So what are you going to do with all the money you have?
You tell me how to turn this into money, please. I have no clue. If you want to check, these are the URLs of Quiz Smalltalk and the GitHub repo of all of Quiz, and in an experimental subfolder there is the code for Morphic 3. So it's all there for you to play with. Huh? Please! Yeah, you're welcome. Okay. Okay, will they pay?
Well.
Okay. Well, thank you. Los micrófonos. Están encendidos los dos, gira.
Go ahead. All right, so I'm very sorry my presentation is not about Smalltalk. I actually was not thinking on doing it because but my project the last 4 years was doing satellites. So for those of you who never heard about this, there is a company called Satellogic here in Argentina that's been doing satellites, and this is my friend Emiliano, who had an idea some time ago. He said, let's do satellites. I want them to be very cheap, I want them to be done very quick, and I want them to be very light, so we can do lots of them. So we can put 300 of them at a time in space. So that's what we want to do. So we got together with some friends, we started working, we got some money from friends, some family, we moved to Bariloche, we did a lot of math to see if what we wanted to do was actually possible. We started doing the satellites. We eventually got a contract with the Ministry of Science here that gave us some more money. They were interested in the project, so yeah, this is just not working. So we've made let me see. We designed the computer. We wrote all the code. We built it over there. And this is the first satellite. It's called Capitan Beto. It's 20 centimeters by 10 by 10. We launched it, I think it's November last year. No, June last year. Yeah, like ages ago. June last year. And inside has a star tracker, that's a camera that looks at the stars. Reaction wheel, that's a motor to turn it around. Communication equipment, a computer that we bought because we wanted the first one to succeed. And since it was the first satellite we did, we didn't know if what we were doing was going to work. So we built what we consider the critical part: the computer, the power system, the structure, and the communication, the radio. But in the same satellite, we flew our first computer, like the first version of our onboard computer. So what we want to do is test in the satellites what's going to become critical for the next generation of satellites. So that's our plan, all right? So it was a success. We launched it, it worked, we communicated, we had lots of problems, but it worked, like amazing, unbelievable. Then we got some more money, we moved from Buenos Aires, from Bariloche back to Buenos Aires. We work in this room, we were like, at the end, like what, 15? Yeah. Too many. Like this is, yeah, 4 by 5. He's helping me because he was there, right? And he's still there. He's working with us. Oh yes, but it doesn't have a screen, so it's so we made a second satellite, and we released all the code for the first satellite on GitHub. We made for the second one, we designed our own solar panels, not the cells, because the cells are very delicate. So we bought them, we designed the solar panels, that's where you put the cell. And we did more things for the second one. We flew, the second one is called Manolito. Yeah, and on the second one we flew the computer, like a second version of the computer we flew on the first one. We flew it on the second one as main computer and only computer. So for that one we already trusted to luck. And yeah, in the second one there is a bigger camera as an experiment that we wanted to test for our third satellite. And there was a radio and a second radio that we wanted to test for the third satellite. But this second radio broke in Earth. So we didn't get to test it. We built half of the power system that we bought for the first one. Half of it we did for the second one. We straight did it and put it as critical. Some sensors and the same radio we used on the first one, but in the first one we had lots of problems with the radio. In this second one we changed a lot how we used it, and we, like, from the launch the radio was changing modes, because for the first one we chose a mode that was unreliable. So on the second one it was supposed to be the most reliable mode, but it didn't work so well. So for the second one we got the radio changing modes every some hours until we decided which mode to stick to. And when we got one mode we liked it, we set it. And so we had the chance to recover from some failures, which is very important. You can go upstairs. So for the third one, we designed a new version of the computer. That's the one in the middle, and that's this is the same thing. So yeah, what's going on? It's still too hard. On the left, you can see there the... Oh, not anymore. Well, that's me on an island. So these are the two first satellites, as I said, 20 by 10 by 10 centimeters. The second one is a bit bigger. That's a full scale, like that's a picture. So that's a satellite, that's Tita. Okay, that's me, and that's the rocket where we put the satellite. We had to go to Russia this time. The previous we sustained it. We had to go to Russia and screen how they put the satellite inside the rocket. I actually got to stand inside the rocket. That was cool. And so we launched this one in June this year. So we launched 3 satellites in 16 months, pretty much. We made it. Well, a bit more for the first one, but that's the timing. And so this one is a bit bigger, but this is sort of the size we wanted to target, because for this one we wanted to have a good camera. So that means a good lens. And a lens, no matter what you do, it takes space. So the quality is directly related to the physical size. So there is nothing, there is not much you could do to reduce that. So as I was saying, this new computer we're flying 2 of them on the satellite. This is how we handle the satellite this is in Palermo, in Buenos Aires. So it's not like in a secret place. It's not so heavy, but we wanted to turn it around, so we hung it. And we don't want it to fall. So this new computer has 3 Linuxes in each computer, and another ARM processor where it runs a real-time operating system. It's free, RTOS. And it has an Ethernet switch, so there is an Ethernet network here and another Ethernet network here, and they are connected. so we can talk from the ground to this real-time operating system, and from there to the Linuxes there. And that changed lots of things, because with Linux we can do a lot more. It's great. Like today, I'm not measuring my time. And okay, all right. And you just tell me. And like, for example, mostly every week or even more, we're uploading new Python scripts to the satellite. Every time the satellite comes by, we upload new Python scripts with new applications and experiments. So this allows us to, in fact, to launch almost without any code in the satellite. And is that right? And then bootstrap from just a shell into a utility that allowed us to upload code, and into a utility that allowed us to upload differential updates and so forth. So, right. Because when we were approaching the date, from one satellite to the other, it was like 7 months, right? Pretty much. So we were throwing things out of the timeline, right? Or this we won't be able to do it. Okay, what do we need? We need to be sure we can upgrade the software. That's it, pretty much, right? That the satellite will survive and that we can update the software. So that's what we focus on. And then we started screwing things. And so one of the things we can do with 6 Linuxes is to log into them all together and configure them all together and screw them all together, like at midnight the day before shipping the satellite. And that's exactly what we did. So there was a guy who was updating the software there, and who was logged into the 6 Linuxes with a tool that's called cluster SSH, when you just type on one window and you type on the 6 of them. And so he wanted to remove /test. So he wrote rf-f/t tab, enter. And the tab worked on just one of the windows. But on the other 5, it deleted the whole thing, right? And we were like, fuck. I couldn't find, well, I found the video, but I couldn't put it together for today. And he was like this, and then he was. And then there's 10 people around him. That's so funny. And today. Yeah, so he pressed Ctrl-C very quick, he screamed, and then we found, like, ls was not there, so we couldn't see what was there. But we found another way around. And at the end, we fixed it, because we found one binary, the QEMU binary, that was linked statically, and we could connect to it remotely on TCP and upload a binary to rsync from the other. Anyway, this is but this is the kind of things you can do with Linuxes. Screw it and then fix it, and this gives us a lot of flexibility in the satellite. And it might sound kind of straightforward, but people's not putting Linuxes on satellites. And this is one of the things we want to do. We want to bring all what we learn in the software environment, like very dynamic cycles. This is a launch from last week. And this is something else we found. One day, one computer was not booting, and we found out that there was no space in the computer, in the satellite. So we removed something and uninstalled something, and we got space. But we only could do it because, I don't know, we predicted it could fail, right? This is a launch last week. He was taking food to the space station. I mean, it could fail. So we were working with that all the time. Like, it may fail. I mean, at one point I actually strongly believe that if we don't fail in many things, we're not pushing the limit hard enough. And we could be doing a bit more. So we are planning on counting on things to fail. Of course, we prefer not for them to fail. But if they do, we gotta find a way to fix them. This is one of the experiments. At some point, one of the things we need to do to take pictures to stabilize the satellite and have it pointing to one place. For safety, because we didn't have time to do it, the satellite was originally rotating all the time. And at this point, we turn on the reaction wheels. This is 4 motors that you control independently to make the satellite rotate or actually stay still. And this is the result that we downloaded from the experiment. So this is the gyroscopic gyroscopes with the angular velocity, and it's flat on 0 during the experiment. And then when we release the wheels, it comes back to the normal rate. And this is another gyroscope, and this is the speed on the wheels. And this is actually a wheel that's saturating up to the maximum speed. And this is something else. The magnetometer, and it's stable during its stable period. So we are doing experiments. This third satellite and the other 2 was for us to learn. And this is the experimentation platform that we have. And this is another data. This is half a day of data that we downloaded. This is temperature. Everybody asked me about temperature, so I put a slide on that. This is 0 degrees, around 0 degrees. And this is around 30 degrees. And these are internal temperatures. This is the temperature on the CPU, and this is the temperature on one part of the telescope. That we wanted it to be stable around 0. We are lucky because we made some numbers, but we didn't really believe it. So this is how it is. And this is external temperatures outside, the most external temperatures we have. And the lower limit is minus 30. And then there is a step down, and that was a particular moment where the satellite was aligned to the sun, so there was not much sun on one side on the satellite, and we were very cold. But otherwise, it's on minus 20, minus 10 is this line, and then 10. But this is the external temperature, and it's still like Earth temperatures. So it's like the system can survive that. It's not too bad. And so finally, we started downloading some pictures from one of the cameras. This is the most interesting one we have so far. Here you cannot see it really well, but we started trying to figure out where this picture was. This is a bit dark, but this is North America. Can you see it? Like here? Right. And so the satellite was on this spot on the orbit. We know it because of the time of the day when we took the picture. And we don't really have very accurate measurement on where the satellite is pointing to. We have a lot of error there. But since we could see the line of the horizon, we could figure out the angle. Because of the height and the field of view, we can figure out the angle. So a guy put the satellite there, put the right angle. It's not a right angle, it's the right angle. And he turned it all around and got pictures and visually compared to find out that we took a picture of this area. That's Miami over there. And this is Cape Canaveral. And Disney World over there. And if this is an enhanced version of this other picture. It's just the same. And there you can see, well, I can see it. I'm probably Juan can see it too. But it's there. I mean, it's the same. And so that's Cape Canaveral, Disney, Miami. Okay, so this is another picture that we took, downloaded. And you can see there are some artifacts. We run the font rendering algorithms. Well, not so much, but Juan ran lots of things on the image, and he could correct it a bit. That's artifacts on the camera, actually, on the sensor, because this is not a very good camera. It's not the good camera in the satellite. So he could correct it, and this is a bit better. We found out that there are lots of clouds all the time. We verified it. We also verified that the Earth is round. Have you? And there are lots of clouds everywhere, all the time. And things get weird and they disappear suddenly. But down here, there's apparently some ground over there. And it's blue because, as you can see, the sky is blue when you look from down to the sky. Well, it's also blue when you look from the sky, from orbit to the Earth. So most pictures have to be corrected for that. and so you do some math on it. And there are more clouds, they're pretty, and more clouds. And when there are no clouds, there's water. We also verify that there's a lot of water. More water. Yeah, that's pretty much it. What we do is we create in the satellite a mosaic, and we download. We're currently doing that. Originally, we couldn't even download a picture. So we uploaded code to create a mosaic of the pictures. We download the mosaic. We pick the pictures we want to download, and then download those pictures. Over there, if you get close to my screen, you can see there are stars over there. So that's a picture of the void. That's not so void. Well, yeah, that's what we want. What we want to do. We want to put lots of satellites. So the next step for us is to do one more satellite in a year, and then after that, replicate it and fly 5, 5, and 5, or something like that. Around 16 satellites in the next 2 years. Yeah, that's my project. He did do the image processing in smalltalk. So there is some smalltalk.
Okay, so now with the interesting, well, I didn't connect anything, so. So, I am Javier Pimas. I showed yesterday the big kernel, and the only thing I wanted to show is a little demo of the project because I didn't have any time left. Yesterday, you are going to remember me because I'm always the last guy to talk before you go to get a beer. So, so I'm going to put this in the other side. Didn't work. First I have to move it, and now I have to take it there. Okay. I don't know. So this is the latest build. I think it's one I've been working on for the last days. I didn't prepare it much to work for a demo because I didn't have time. So what you're going to see may explode in my face, but I think it's going to work a little. So the only thing that the thing interesting is, for example, looking. For example, here we have the basic libraries that we made. There is b.bsl, which is the main executable file. This is a Smalltalk library packaged inside the PE executable format. It occupies like 5 megabytes. It could occupy a bit less if I wanted to. And what I'm going to do is just show how it works. You can see that this is running Linux, but we work with Wine, so we can run executables. For example, I could do, well, what I could do is run the tests, some tests, and these were run on. And if it shows, it will show in my screen, but believe me, this has just run. So here we have all tests running and passing. This is just the minimal tests. While the mouse disappears. Okay. And then what I can do is also to execute the main executable with some command. For example, like I say, load and run the slopestone runner. So I'm going to run some benchmark. So there it's running, and it runs. So you can see the times there, like, I don't know, byte-array creation, everything. I can also show the same, but running on the host VM. Everything gets in the other window. Doesn't work. The mouse doesn't work. Okay. No. No. What I can do is move it to the other window and bring it again. Maybe. Okay, it worked. So here we have something. So for example, I don't know, if we look at the overall result, it's running 162 milliseconds. There it ran in 181. Okay, so it's running like, I don't know, this is 10%, around 10% slower, a bit more maybe. We can also run the console. So welcome to me. We can write anything here. I don't know, like 3+4. It's working a bit slow. I don't know why. It takes a bit. Then, if you run it again, you have to consider that for the first time, it didn't load the compiler nor the nativizer. So, for the first time, when it compiled this, it had to previously load the compiler library and the nativizer. So that's why it took a bit longer. If we run it now, it's faster. I don't know why it's taking only the first two commands, So I'm going to run it again, and we can run, I don't know, we can give it any order we want. For example, I don't know, like 20 factorial. Thanks. I think that's all. If you want to see something else, you can ask. But that's all. Thank you very much.
Are we done? Oh, yeah. See you in the dinner.